Hey there, in this video we are looking at the selection sort algorithm, and there's a pretty good example of this in section 8.4 of the Gaddis textbook. So selection sort is going to be the second sorting algorithm that we investigate here. In the last video we looked at bubble sort, which is the simplest of all sorting algorithms actually, which is why we start off with that. But having looked at that, we said there's a number of limitations to bubble sort. One, it has nested loops, which is going to cause quite a large number of iterations most of the time. And secondly, it does an awful lot of swapping jobs. So among the examples we saw last time, if the smallest thing in the array starts off at the end of the array, and it really needs to get to the start of the array, every iteration, it only goes forward one step. You move it one step forward and another step forward. And every time you do that, you have to do this copy, copy, swap job. Copy, copy, swap, copy, copy, swap. So it winds up doing quite a lot of work as it moves an element just one step at a time across the bubble sort. And we also said that writing to memory, a copy, is more intensive than just reading from memory, it takes more time. So all of those copies and all of those swaps wind up taking quite a bit of time on the CPU. So we're hoping we can possibly do better. Now, the first improvement that someone might say in a situation like that is, instead of having the smallest thing move one step at a time, why not just find the smallest thing and put it in the right place? Why not just put it in the right place to begin with and save all those copies? And that's the essence of selection sort, is you are going to find the smallest thing and just make one single swap and put it in the right place in one step. And hopefully that's going to save a lot of time. Let's think about that a little bit more deeply. So the basic idea for a selection sort is you're going to search the whole array and do a find the smallest job like we covered, like we reviewed back in chapter 7, kind of standard algorithm. You're going to locate the smallest element in the array and just swap it with the element in position 0, because that's where it goes. It belongs at the start of your array. And then you're going to search what's left over in the array, find the next smallest thing, and put that in position 1, because that's where that belongs. And repeat to find what belongs in position 2, and repeat to find what belongs in position 3, and so on and so forth. So on every single iteration here, you're just going to do one single exchange, one single swap, and every time you do that, you're putting a particular value in exactly the correct ending location. And hopefully that makes sense. Let's look at the pseudocode version of this. And this looks a little bit more complicated than the bubble sort pseudocode, but hopefully we can make this understandable. So it starts off with this for loop with this variable start scan. And if you can really understand what that start scan variable is doing, you're going to understand what this code is doing. The start scan variable is really kind of doing two jobs to my mind. This for loop, what it's there for, this outer for loop, is really saying, I'm going to find what belongs in position 0 and put it there. And later on, I'm going to find what belongs in position 1 and put it there. And that's what start scan is really there for. It's indicating which index you're trying to find the correct value for. What am I trying to fill on this particular pass? That's start scan. So to my mind, personally, if I'd written this code, I would have named that variable with a different name. I would have called it slot to fill. And the first pass through, I'm trying to fill position 0 with the right thing. And then I'm trying to fill index 1 with the right thing. So to my mind, it's really the slot that you're trying to fill. And when you get down to the end of this function, the second to last line there, it says set array start scan to the minimum value. So you're going to be finding the smallest thing and putting it in array index start scan. That's what it's really for. But it does have this second job. For example, if you're trying to fill index 1, you have to do this find the smallest job, and your scan is going to be from 1 to the end of the array. I've already got, presumably, the correct thing in position 0, so I'm not worried about that. On this particular scan, I have to scan index 1 and 2 and 3 to find the smallest thing. So yes, in addition to that other thing, it is also the place where you start your scan for the smallest thing. So that's why they called this start scan, and it's true, that's where you're starting the scan on each pass, but even more importantly to my mind, it's the index that you're trying to fill right now. Okay, so we'll do that decision for position 0 and 1 and 2 and however many things you have in the array. Now, once you get into the body of the loop, most of these lines of code are really just the find the minimum job. We've seen that before. Again, you can review that back in chapter 7, standard algorithm here. So hopefully this looks familiar. The first two lines you're setting up, you're initializing for the find the minimum algorithm. And of course you have a variable called min value here, which is going to be storing the smallest thing we've found so far. And of course you start that with the beginning of the section that you're scanning right now, which is array start scan, like we just said. They're adding another thing here. In addition to that, they've also got a variable called min index to store the location of the smallest thing. So they also have that. That's really the only addition here. Once you've got that set up, you have this inner for loop where you actually do the scan to find the smallest. Now you've already looked, you've already inspected array bracket start scan. You don't have to do it again. So this starts at start scan plus 1 to the end of the array. Once you're done with that, you've looked at everything in the array. And you have this standard job here where if the thing you're currently looking at, if array index is less than min value, apparently you've just discovered a new smallest thing. So you record the value in min value, and you also record the current index in min index. Right? Just, again, standard find the smallest job. So once you're done with that inner for loop, the last two lines just do one single swap. So as you can see here, wherever you find the smallest thing, you're going to swap in what's in the first location. Okay, so swap that in here, and then whatever is in the smallest location, you put that in the first position. Start scan, which is the beginning of the position where you're currently scanning. Now, normally for a swap like this, you need a third variable to do the swap. Fortunately, the way this is set up, you get that for free because we already put the smallest value in min value. So that's why the very last line really does the job we're trying to do here is whatever the minimum value is, put that at the beginning of your array. Put that in start scan, the position that you're currently considering. So you find the smallest thing and put it in position 0. Find the next smallest thing, put it in position 1. The next smallest thing, put it in position 2. Again, that's really start scan being filled in there, and that's how this code works. Now you notice that this still has nested for loops, right? That was something that we were critiquing in bubble sort because the multiplication causes a large number of iterations, and I guess we're not getting away from that. There's still nested loops here, so we'll probably have to think about that kind of closely. Here is the C++ code version of that, a pretty clear translation. Similar header that we had in bubble sort. It's a void function. It's not returning anything. This is called selection sort. You're passing in the array to sort. Again, C++, you need the two parameters. The first one is the array that you're interested in, really the address of where the array starts. And the second parameter is the size of the array, so the function knows where it ends. And they declare these three variables for start scan, the position that I'm trying to fill right now, as well as min index and min value for the find the smallest job. The outer loop start scan is going to go 0 and 1 and 2 and 3 as you fill in each one. Lines 41 to 50 are the find the smallest job with the initialization and the for loop for the search and the if statement to determine whether something's smaller, like we said. And again, lines 51 and 52 are the one and only swap that happens per pass. So I emphasize that again, bubble sort has the swapping code in the innermost loop, right? So you possibly do swapping and swapping and swapping because it's in the innermost loop. So at least we've moved the swap code out of the innermost loop, and you're not going to do it a whole bunch of times. You're just going to do exactly once per pass of the outer for loop. So hopefully that's the thing that's going to save us some time in this function. Okay, and now just like we do with all these algorithms, we are going to hand trace this to prove to ourselves that we really understand how selection sort works. So there's the code in the small frame there. I'm going to use the exact same example we used for bubble sort. I'm going to take this array that's holding 11, 2, 29, 3. Obviously it's size 4. And we're being asked to hand trace the values in the array at each iteration of the outer loop. And as we do that, we're going to highlight the part of the array that's no longer being scanned. So keep track of this same kind of table here. How many steps have I taken? As you get into this function, before you enter the for loop for the first time, I'm going to call that step 0. And the array is starting off at this 11, 2, 29, 3 before any changes get made. So you get to line 39 and start scan is being set to 0, which is really saying position 0, we're going to find out the correct thing that belongs here, the first thing. So this gets your initialization in lines 41, 42. It goes through scanning starting at this position. So it scans position 0, 1, 2, 3, finds the smallest thing. Hopefully you know how that works. And obviously the smallest thing here is the 2, which happens to be an index 1. So you're down on line 51 once that's done, and you basically just swap these two things. So you swap the 2 into position 0 where that 11 is, so the 2 and the 11 just flip like this. And at the end of step 1 here, the array is going to be 2 and then 11, and then the 29 and the 3 that didn't change anything. Now, once I'm done with that, again, 2's in the correct location, right? The smallest thing obviously goes in the first location. We're not going to worry about that anymore. I have that in boldface to indicate that. So I come back to line 39, and now start scan is going to be 1. I'm going to find the correct thing to go in position number 1. So as we scan this, the find the smallest code starts from 1. We're going to look at 1 and 2 and 3 and find the smallest thing there. Now, obviously, that's the 3. So once that job gets done and you're down on line 51, you take this 3 that's currently sitting at the end and you swap it with start scan, which is 1. Again, that's line 52. Array bracket start scan, position 1, which is what you're trying to fill here, is going to get that number 3. And that gets swapped with what's currently here, which is the 11. So at the end of this step, you're going to be looking at 2, 3, 29, 11, because all you had to do is just swap the 3 and the 11. 2, 3, 29, 11. And you're back on line 39, and now you don't need to worry about this, you don't need to worry about this. I've got that in boldface. Start scan is going to be 2. We're going to find the correct thing to put in position 2. So you just need to scan the array from position 2 on, 2 and 3. What's the smallest thing there? Obviously 11. So you get down to line 51, 52, you flip these this time, and now you're going to be looking at an array that's holding 2, 3, 11, 29. And now you're done. You get back to line 39 for what it's worth. Start scan is going to become 3. You check in that conditional there. Start scan is 3. Size minus 1 is also 3. 3 is not lesser than 3. And the loop ends and you're done with the function. As you can see here, it does actually correctly sort the array. So hopefully this will be faster because on each iteration, it's very predictable. You're doing exactly one swap. And every single time you do that, every time you do a swap, you're definitely putting a value in the correct finishing location. So hopefully this will be more efficient. The other thing that you see here is that since the way that the outer loop works, you're definitely going to put the correct thing in this index once per iteration. So as a result, you're going to have a very predictable number of iterations. Specifically, if I have an array of size n, I'm going to have guaranteed n minus 1 iterations. Like in this case, I have an array of size 4, and sure enough, we had 3 steps. That always happens guaranteed. All right, so a couple of advantages of the selection sort. Let's talk about some trade-offs there. So is it faster? Well, yeah, it's going to be, but it's not going to be cosmically faster like binary search was versus linear search, because we still have those nested for loops. Right? We still have those nested for loops. We have the outer loop that finds the correct thing for each index. Well, obviously, if I have 4 things, that loop's going to have to go 4 times to find the right thing. Now, technically, it was 3, because once you have everything but the last one, by deduction, the last thing has to be the biggest, and you don't have to do any work for that. So technically, it's n minus 1 times for the outer loop. But let's round it off and just call it n to make the numbers simple. The inner loop, the first time you do that, you definitely had to search everything in the array. So the inner loop definitely went n times, at least the first time you do it. So worst case scenario, the outer loop happens about n times. Worst case scenario, the inner loop happens n times. And again, with the nested loops, n times n is n squared. So we would say that this function can take up to n squared iterations, which is not any better than bubble sort actually. But the advantage is each iteration only does one single swap of the outer loop. Hopefully it's doing a lot fewer swaps than bubble sort, and that is where the speed advantage is going to come from. Now, again, this is not a complete clean sweep for selection sort. Binary search is just so much better than linear search, there's no question about it. This is not, it's not all the time better. Here's an example of where it might not be better than bubble sort. If you hand it an already sorted array or an array that's close to it. Selection sort is still going to have to do that number of iterations. If I hand off a 20 item array and it's already sorted, selection sort will still do this whole job and do 20 iterations before it's done. But you know, the way that bubble sort works, if you hand it an already sorted array, it goes through it one single time, discovers that it's sorted, and then would be done in one single pass. And it would actually, in that case, it would actually be faster than selection sort. Obviously, that's a rare situation. I wouldn't bet on that ever happening in normal usage. But maybe if you're in a situation someday where you know, I've got a sorted array, I added one more thing to it. In that exceptional case, bubble sort would actually be faster. So you kind of want to be cognizant about that. You might actually want to use either one. But most of the time, selection sort is faster. We should dig in to find exactly how much faster it is. Okay, so what I'd like to do next is actually do a comparison of our two sorting algorithms, bubble sort and selection sort, to get a concrete feel for exactly how much faster selection sort is. So as we've done in the past, I have a folder here with a code file that I've made called sortingcomparison.cpp here. And basically what I've done here in this code file is I've just put in the code to both the bubble sort and the selection sort. So open this up here. And you can see here that I have prototypes on lines 19 and 20 to both bubble sort and selection sort. I've just copied in the code directly out of our lectures from the Gaddis textbook, and it's down below in this code file actually. So if you want to see the specifics, just go look in the book. And what this is going to do is whichever one I want to use for my sorting function, I'm going to make a fairly large array, size 50,000, with just a bunch of random integers. And I'll call both, and we'll use debc++ to time how long it actually takes to sort those two things. So I've got bubble sort and selection sort. Here is the prototype to my function called fillRandomArray that just takes the big array and fills it with random numbers. Let's go take a look at that just for a second. So fillRandomArray comes in. Hopefully you remember how to use random numbers in C++. That's back in chapter 3 if you need to review that. But to make a long story short, you seed the random number generator, usually with the current clock time, which is a call to the time0 function. And once you've set that up, I have a for loop here that just goes over everything in that array and sets each one of those things to a call to the rand function, which is how you get the next random number. Right? So at that point, everything in the whole array just has a bunch of random integers. So my main function here is to make the big array, size 50,000. It's going to print out making a random array and sorting it, obviously. Fill it with random numbers, like we just said. And then, at least to begin with here, I'm going to call the bubble sort function. And we will see exactly how long it takes to sort a 50,000 item array, at least on my system, right? There's faster or slower computers in the world, but we're just using this to see the proportional difference between the two systems. Okay, so I will compile this, and over in the folder here, obviously, I'm going to get sortingcomparison.exe, and now I can run it, and let's see how long this takes for bubble sort to sort a random 50,000 item array. Get that on screen here. So it's working, and it's working. Bubble sort is working. Okay, and it's done. So it managed to sort that in 5.7 seconds. Right? I mean, you know, pretty fast, but you still, as a human being, I still had to kind of pause for a second to kind of wait for it. So 5.7 seconds is what we're getting for that. Now, I'm going to go into my code here on line 28, and all I'm going to do is just change the call to bubble sort to a call to the selection sort function. And obviously, I have to recompile this. Basically the same idea. Get, again, a 50,000 item array with random numbers. Try to selection sort it, and we'll see how long this takes. And again, it pops up on my other screen. I'm going to have to bring it on the screen here. And, oh, it's already done. So selection sort did that job in 1.082 seconds. So the first one was a little bit more than 5 seconds. And the second attempt only took 1 second. So it only takes about 1/5 of the time, at least on this experiment. Right? It took about 1/5 of the time that bubble sort did. And I find that that tends to be about what happens. You can try it with larger arrays. You can try it with smaller arrays. It doesn't have the exponential speed up that binary search has compared to linear search. Again, binary search saves you 99.9998% of the time with a million item array and just gets better from there. Selection sort is saving you about 80% of the time based on this experiment. And it doesn't get exponentially better. It's almost always taking about 1/5 of the time in my experience. The other thing I suppose someone could possibly point to in this experiment is that the two things weren't actually the exact same array. Like I filled one randomly and I filled the other array randomly with presumably different numbers. So someone could say maybe a better experiment would use the exact same scrambled up array for both. But I find even if I repeat this a bunch of times, that ratio is about the same. They take about the same amount of time no matter what the array state is. And it tends to be about 1/5 of the time. Okay, so as an estimate, as an approximation, that's how much better selection sort is than bubble sort. It's better, clearly, for a large array like this, but it's not cosmically better like binary search is compared to linear search. So maybe there's still room for improvement. Maybe that's something we should investigate in the future. Okay, so this brings us to the end of Chapter 8 with our introduction to searching and sorting. So for students in my class at this point, I asked them to do this homework that's on this slide. My students should read the book chapter that we just covered to get all the nitty-gritty details that we didn't have time for in the lecture slides. I would recommend that they practice with the review questions at the end of Chapter 8. There's some questions like fill in the blank and true false that resemble at least some of the questions that I would put on my tests. And my students will also have their next programming challenge out of Chapter 8. So you should go to our learning management system, see exactly what I'm asking you to do out of Chapter 8, write your code, test it, of course, and submit it before the due date. So kind of standard stuff that we do at the end of each chapter. Now, one thing I want to emphasize here is that we've just begun learning about like our sorting algorithms. We saw bubble sort, we saw selection sort. There are more sorting algorithms in the world. There's things like quick sort and merge sort and insertion sort and tournament sort and a bunch of other things. So maybe in the future we'll come back and say, are there other improvements that we could make that would be even better than selection sort? But before we do that, we're going to need to learn more stuff about C++ and more technology and more ways of writing programs actually. So some number of weeks are going to go by and we will probably come back to this and think about investigating maybe other sorting algorithms near the end of the semester. But that'll be a while down the track. Don't entirely forget about sorting. It's so important. We would still like to make more improvements if we can. And the next lab, when my students and I are in person, will be this one, this working with the selection sort lab. Very similar to what we did with bubble sort, actually. We get a code file that has a complete working program. The program initially sorts an array in ascending order. Job number 1 is modify it so it sorts the array in descending order. That's pretty simple. And then we're going to modify the program again so that it prints the array once per iteration of the outer loop. Hopefully we get a printout that resembles what we got for the hand trace, confirm that our understanding is correct about that, and of course test your program with the same array that we did last time. And we can compare and contrast with what happened in bubble sort, hopefully, and get a little bit more practice about what we expect to happen with this, and can we hand trace it and predict what the program's actually going to do. So hopefully that's good practice before our next test. Now, in our next video, we're going to start with Chapter 9, obviously, which is on the subject of pointers. And boy, is that important. That's incredibly important. Pointers are a major part of how programming languages work really under the hood, how C and C++ work. And they're really fundamental to how computers and even just like a CPU processor works in the first place. So advanced programmers definitely need to be aware of pointers. And I'll say this. For a lot of people, the first time they see pointers in their programming class, it comes off as very confusing. And I'll even say that the first time I saw pointers, I was pretty confused by it. But they're so important, we really have to understand it. It's going to be part of our work in C++ for the rest of the semester. And it's probably going to be part of your work as long as you're working in C++. It's something that you're going to have to consider and use to your advantage. So hopefully we'll be able to make that clear and concise in our next video, and I'll really look forward to digging into that incredibly important subject, and I'll see you then for that.